Hey kids, this is a description of how to solve the problem. I'm not necessarily going to do the calculation, but I will just describe what to do. Okay, so the first problem is it wants to approximate the rate of change. So remember, this means we're going to find some kind of slope of the number of vehicles in line. So what this is L of t. That's the number of vehicles in line at t equals 10. So I don't have a function for L of t, but I do have a table of values. So if I want to approximate the slope at 10, I want to find the slope between 2 points. Now here is 10. So I can find the slope between these 2 points, and that will give me one answer. Or I could find the slope between these 2 points because it's something that is near 10, and that will give me another possible answer. Or finally, I could find the slope between this point and this point in order to approximate the rate of change. Now remember the units. I like to draw this little graph, and this is going to be L of t. If I notice in my x position is time, which is minutes, and then L of t is going to be vehicles. So my y value is going to be vehicles. So if I want to figure out the units for this, the slope is going to be vehicles over minutes. Is getting into now find the rate of change of the wait time. Now the wait time is this function right here, when 60 vehicles are lined up. So what I want to do is I want to figure out the derivative. So I want to find w prime of x, okay, then plug in 60. So I want to find w prime of 60. Now when I take a derivative here, pay attention to the chain rule for what is inside the function. I want to indicate units of measure. So again, I like to take a look at w of x. Now w of x, if I'm going through, pay attention to x, which is the number of vehicles. Okay, x is a number of vehicles, so x here is going to be the vehicles. And w of x is going to be seconds. So when I figure out my slope, remember my slope is dy over dx, or it's going to be my y's over my x's. So my units of measure is going to be seconds over vehicle. Okay, so that is part B. Jumping into part C. So part C, I want to approximate this integral using a trapezoidal sum. So I want to approximate the integral L of t. So this means I'm going to be using my table. Remember, my graph for this, again, L of t, where t is going to be minutes, and L of t was vehicles. So what I'm doing is I want to approximate the area under the curve using a trapezoidal sum. The area equation for a trapezoid is 1/2 the height times base 1 plus base 2. And I want to go all the way from 0 to 60. So I'm going to cut it off right there. So my first trapezoid is going to be right here. The height is going to be 10, base 1 is 10, base 2 is 60. My second trapezoid is right here, so that height is going to be 20, base 1 is 60, base 2 is 100. And then repeat the process with the bases and the height going all the way through in order to get your calculation. So we just got to remember that I'm going to sum all of that up. So I have 1, 2, 3, 4 trapezoids. And then my units, since I'm finding area, is I multiply these together in order to get area. So my units for this are going to be vehicle minutes. Okay. Here, I want to find the fewest number of times in which L prime of t must equal 0. So again, I'm going to be using the table. Now, if I take a look to what L of t is doing, here I am increasing, here I am increasing, here I am decreasing, here I am increasing, here I'm decreasing, and here I am decreasing. So if I'm taking a look at how many times must the derivative equal 0, first I got to understand that this is a nice smooth curve. It's a nice smooth curve because it's a twice differentiable function. So if I have a nice smooth curve that's increasing then decreasing, so right in here is going to be the first area in which I am going to get the derivative equals 0 because I'm going up and then I'm going down. In here, I am decreasing then increasing, so there's another place where I have to get the derivative as 0. And then finally in here, I am going from increasing to decreasing, so there are 3 places in which I am going to get a position in which the derivative equals 0 because I have a nice smooth curve and I'm going from increasing to decreasing, decreasing to increasing, and then increasing to decreasing. E, and this one is a little tricky because there involves a few things that we got to do with W of x right here. So I want to figure out the rate of change of the waiting time in line. Okay, so indicate units of measure and explain your reasoning. So basically what I have here is I have W, which is the wait time for the vehicles at a certain time t. So this is the function that I'm dealing with, the wait time for the vehicles at a certain time. So this is what I need to eventually take the derivative of because I want to find the rate of change of this equation. So when I take the derivative of this, that is going to be the chain rule. So it's W prime of L of t times L prime of t. And now these things, oh, not 10, but of t. Okay, so then I want to figure out at time t equals 10. So that is going through W prime of L of 10 times L prime of 10. Now L of 10 is going to be right here, so this is going to give you 60, so I get W prime of 60. And then L prime of 10 is going to be the calculation from letter B. So this is going to be from earlier, part B. But it's just understanding how all of this comes together, find the rate of change of the waiting time for the vehicles at a certain time. So that is a pretty tricky problem, putting that all together. And that is what you need to do in order to solve it out. If I were to go through and figure out units for this, remember you are multiplying W prime, which is seconds per vehicle, times L prime, which is vehicles per minute. So what it turns out to be is seconds per minute.